Welcome back to Calculus 1. In this lecture, we're going to introduce a very useful topic, but also one of the hardest topics for students to understand in Calculus 1, something called optimization. This is our kind of second time coming up on what you would call a word problem. Now we're going to throw calculus back into this for some very challenging problems. All right, so the idea of what this technique called optimization is it's a way to find a maximum or minimum value of a certain quantity that might come up from, let's say, a real world problem, something that might come from within one of your science or engineering courses, or maybe coming from economics or a business model of some sort. All right, now this does get very complicated, but I want to kind of put this on a simple foundation first. Let's just consider some various quantities that we might be interested in optimizing, either finding the maximum value of it or finding the minimum value of it. Certain quantities you would want to do a maximum, other quantities you would want to find a minimum. Let's take a look at some of those. So let's think from, let's say, a combination of your science courses, specifically physics or chemistry, your engineering courses, or maybe economics. Let's consider some examples of things that we might want to maximize. Now, just give yourself a few seconds and think of some quantities that you would want to maximize. There's kind of no wrong or right answers, but there's some standard ones that we'll take a look at. All right, hopefully you came up with a short list. For various problems, we might be interested in maximizing, let's say, the area. Maybe we have a fixed amount of, let's say, fencing, and we want to design an enclosure of maximum area. Maybe we have a certain amount of plastic, and we want to kind of design a container made out of that plastic that has maximum volume. And let's say from like a business or economics course, you might be interested in maximizing profit. If you're dealing with various aspects of engineering, you might want to design something with a fluid flowing through it that maximizes flow rate. Could also be the flow of traffic, which is a kind of a big place where mathematics is used in mathematical modeling for traffic, maybe designing highways, on and off ramps that maximize the flow of traffic. All right, let's think of some examples of quantities that we would want to minimize. Again, I'll give you a few seconds to kind of write down a short list. There's, again, no wrong or right answers, but again, standard things that we'll be looking at through our Calc 1 course. All right, hopefully you have a short list. If we think of some examples of quantities that we would want to minimize, well, let's say we are traveling from one point to another, we probably would want to do so in a way that minimizes the distance traveled. All right, also if we're traveling from one point to another, we would want to minimize the travel time. If we're producing something in like a factory setting or whatever, we would want to produce things while minimizing the cost of production. And if we're dealing with kind of various topics in physics and chemistry, we might be interested in a kind of reaction or something that kind of evolves in time that minimizes the energy involved. All right, now this maybe all starts to sound very complicated. We're not going to assume any background knowledge in physics, engineering, anything like that. But this just gives you some examples of, there's a wide variety of quantities that this mathematical procedure called optimization applies to. It is extremely useful, but at the same time, it's also very complicated. Now, to get to some of the actual real world problems, something that might be solving in kind of your junior and senior level science and engineering courses where there are practical problems that you can solve. As you get into more real world problems, the mathematical models usually get a lot more complicated. And it's kind of often that you get a real world problem that requires at a minimum of multivariable calculus, calculus 3 usually. That's because a lot of quantities might depend on several or multiple variables. Now for our course right now, Calculus 1, we can't go that far since our course, we're still learning about single variable calculus. If you're continuing through the calculus sequence, calculus 2 also deals with single variable calculus. So there's still a lot to be learned for single variable calculus before getting to multivariable calculus. Everything we look at will depend on a single variable, and we'll mention that again as we go. So don't worry about multivariables. We'll find a way to reduce the number of variables through the problems we look at in this lecture. Now let's go back to earlier in the course when we started talking about absolute maximums and minimums, and then shortly after that, critical points and local maximums and local minimums. We maybe necessarily didn't call it optimization, but we did have a procedure for finding the absolute maximum and absolute minimum values of a function on a closed interval from A to B. If you think back, we started off by finding the critical points of the function. So that required us to calculate the derivative, see where it was undefined or equals 0. And we only consider any critical points within that interval, A to B. Then we take a look at the function values at each critical point and each endpoint, A and B. And from that list, once we've plugged them into the original function, the largest of those values corresponds to the absolute maximum, the smallest corresponds to the absolute minimum. There was something we called the extreme value theorem that guaranteed the existence of an absolute max and absolute min for a continuous function on a closed interval. The extreme value theorem is going to kind of be at the heart of the content we learned for this lecture, but we're not going to really bring it up since it kind of gets to be very technical. All right, so this procedure, what we addressed with finding the absolute maximum and absolute minimum values, that is optimization, but just from the mathematical perspective. For these questions, we were always given the function f of x and given the interval a to b. Essentially, what we're going to be doing with our problems is we'll be given a traditional looking word problem and have to translate it into the function f of x in order for us to start the problem, which we'll be doing this optimization procedure for that function, find the critical points, and then proceed from there with these steps. All right, now, again, this will get very complicated, so just go into this lecture expecting that. The problems we look at in this part will be kind of on the simpler side. Part 2 of this lecture would be some more challenging examples and problems. All right, now, before we get to those, let's take a look at a few brief steps for how this works. Very similar to how we approach steps for related rates problems. Those were our first examples of seeing word problems involving calculus, but very different. Earlier, for related rates problems, we were looking for the effect of a given rate of change on some other quantity's rate of change. These problems, we're just looking for a certain quantity, the absolute maximum or absolute minimum of that quantity. Very different problems, but both look like word problems. All right, now there's a few steps to kind of be able to set up everything. We're typically going to want to, in step 1, try to draw a sketch. For a lot of problems, if you have a sketch, that kind of puts you on the rest of the path to solving the problem. All right, in order for us to build up and get a function, f of x, like stated in the previous part a few minutes ago, functions are made out of variables, so we need to introduce variables of our own choosing. They're typically not going to be stated in the statement of a problem. We have to choose them ourselves. So if we're dealing with, let's say, kind of a geometric object and there's various side lengths, maybe for a rectangle, might make sense to call the length and width L and W and kind of choose variables appropriately for the quantities involved. All right, once you have your variables, in step 3, you want to determine which quantity is being maximized or which quantity is being minimized. This is usually stated at the end of the problem, which we'll kind of point out in some examples that we'll be getting to. Once you've determined what quantity that you're maximizing or minimizing, or what quantity you're optimizing, you're going to want to, in step 4, use your variables to find a formula or equation for the quantity that's being optimized. If you're asked to maximize area, you would want to find a formula or equation that says something about area. If you're asked to find or optimize volume for some object, your equation or formula should be something involving the volume. All right, most problems state that in the question. The tricky part here, the important part, goes back to what we mentioned in the beginning. We're dealing with single variable calculus. So once you come up with your equation or formula, you have to make sure that that equation or formula only depends on one variable. And we'll be boring. That single variable we're usually going to use is x, but it doesn't have to be. Now let's say you come up with an equation or formula that has more than one variable in it, or more than one independent variable, if I get technical. Then what we're going to have to do is somehow reduce those variables down to just one. And the way this works mathematically, we use something called a constraint. And this is just a technical term. A constraint is basically any equation that relates your variables together. So pretty much if you have more than one variable in your equation or formula, find another equation that you can solve for one variable in terms of the others to plug it into your formula or equation to get it down to a single variable. If you continue on to multivariable calculus, calculus 3, you'll see this idea of what's called optimization with a constraint come back, but that's best left for Calc 3. All right, and once you have kind of your equation or formula found from step 4, now you're basically ready to pick up with the optimization procedure. Now you have a function of one variable, and you can apply your optimization procedure for your function, find its derivative, find the critical points, and proceed from there. A lot of the questions we look at, for whatever reason, only usually work out to have 1 or 2 critical points. So it makes it very easy to check from your critical points which correspond to the absolute maximum or which correspond to the absolute minimum. All right, now before we move on to the examples, and we'll take a look at 2 of them, maybe pause the video to copy these down so that way you can refer to them through the various problems that we'll look at. All right, now before we get to example 1 and example 2, I just want to make you aware of where most students struggle, and this is certainly to be expected. The most difficult part is step 4, coming up with the equation, formula, or what we are after, a function of just one variable. That's where your sketch comes in. The first few examples that we'll look at in this lecture, this part, will be on the simpler side, basically just needing to know the area of a rectangle and volume of a rectangular box. The examples we'll take a look at in part 2 are going to be where it gets a little more complicated. All right, with that in mind, let's get to our first example. Example 1, this is a standard example that I'll say pretty much most Calculus 1 students encounter in some variation or something very similar. All right, and the question is, a piece of wire of length 8 feet is to be bent into the shape of a rectangle. We want to find the dimensions that produce the rectangle of maximum area. Now you might be able to take a look at the end, the very last 2 words. What we're trying to do is maximize area. So what we want to go through those various steps is we want to find a function, formula, or equation that says something about the area of a certain rectangle. All right, now let's take a look at kind of some intro ideas to this problem. So we have pretty much a straight piece of wire of length 8 feet, and we're going to bend that, connect the two ends there. You can see the little dots at the end. We're going to kind of connect those together. Of course, to get a true rectangle, we want that gap to be eliminated. I just have that gap sketched there in the rectangle, so that way you can see the ends are coming together. All right, so it seems pretty simple. There's a lot of variations of this. There might be a variation that says something about a farmer having a fixed length of fence, and he wants to design an enclosure for, I don't know, let's say his majestic Ecuadorian alpacas. All right, now there's a few different possibilities for this kind of rectangle. We don't need to do this for the problem. This doesn't count as our sketch, but I at least want to make you aware that there are several different configurations that we might be interested in. So we have a fixed amount of wire of length 8 feet. One possible arrangement is if, let's say, we make the length 3 feet. So it's 3 feet on the top and 3 feet on the bottom. That leaves a total of 2 feet left. Divide that 2 feet in half to get the sides there. They would be of side lengths 1. Now with those dimensions, a 1 by 3 rectangle, you get an area of 3, or 3 square feet. All right, well, we can kind of lengthen I guess not orientation, the height, from 1 unit to 1.5 units, or 1.5 feet. We also have to reduce the length, and a set of units here that would work, or dimensions, would be 1.5 feet by 2.5 feet. If we multiply length by width, we get the area here comes out to 3.75 square feet, which is bigger than 3. All right, can we make the area a little bigger? Well, we could kind of make the length and the width or height equal and take a look at a 2 by 2 rectangle or square. And in that case of a rectangle with dimensions 2 feet by 2 feet, you get an area of 4. And that is, again, bigger than the area 3.75 right before. Now, you might be thinking, is that the maximum area that we can get for a piece of wire of length 8 feet? We'll see. We could also go to the extreme, the last configuration there, where we make it really, really long, but at the same time, really narrow. And as it turns out, if we say for that configuration, go with, let's say, a length of 3.5 feet, that leaves kind of 1 foot left for the height there. So our other dimension would be 0.5, or half a foot. If you multiply 3.5 by 0.5, you actually get a smaller area, 1.75 square feet. So how do we find the maximum area? Is 4 the maximum area? Are the dimensions that produce that rectangle of maximum area a 2 by 2 rectangle? Or is there some configuration out there that we haven't thought of yet? Well, the procedure known as optimization will give us a conclusive result on that. Now let's go ahead and try to apply some of those steps. So let's first draw an arbitrary sketch, just a rectangle. For the rectangle, what's relevant are its length and width. So let's call each of those dimensions or quantities. Let's call 1 the length x and the height or width y. You could also use L and H, but we'll keep it simple for the usual variables we use in mathematics, x and y, but we could use any variables. All right, so we have 2 variables. What we want to think now is, what quantity are we optimizing? So what quantity are we looking for the maximum, or what quantity are we looking for the minimum of? And it's stated at the very end of the problem, we're trying to produce the rectangle of maximum area. So through this optimization procedure, we're trying to maximize the area of that rectangle. Now, how does that help us? Well, with our variables, x and y, how would we define the area of that rectangle? Well, that's simple. Once you have the length and width, you just multiply them to get the area of that rectangle. So we can say here, our area formula or equation is A, the area, equals x times y. There's an immediate problem that contains two variables. What we need to do is somehow eliminate one of those variables, either x or y, down to just one of them, so that way we can apply what we're learning about, the techniques of single variable calculus. Now, there is some information that we haven't used yet. Maybe pause the video to give yourself a little bit of time to think of that. What information haven't we used yet? Think of mathematics like a game. Most problems you're given just enough information. You're not given too much or too little. Think about what information we haven't used. All right, well, what haven't we used? We have a total length of wire of length 8 feet. Now we're bending our straight piece of wire into a rectangle. That straight piece of wire forms then the perimeter of that rectangle. So our constraint, which basically comes from the perimeter, our perimeter for our rectangle sketched in the upper left corner there, would have kind of length 2x plus 2y. So what we get is an equation that relates our variables, x and y together. The perimeter, we'll say 2x plus 2y has to equal 8, since we're trying to use the entire length of our wire to create the rectangle. Now, how do we actually use this constraint in practice? Our area function depended on two variables. Give yourself a few seconds, solve that constraint equation, the perimeter equation, solve that for y. All right, that should be pretty simple. You can subtract 2x and then divide by 2. You should get y comes out to be 4 minus x. How we use this is by plugging it back into our area formula to eliminate two variables down to one. If we replace y with 4 minus x, we get our area function. And notice I'm writing that in function notation, a, the area, as a function of the side length x, equals x times 4 minus x. The 4 minus x, that was what we found from the constraint equation, the perimeter for y. All right, and we can multiply that out, just distribute that x into the parentheses, and we get our area function as 4x minus x squared. If we think about what kind of range of values x can have, recall we technically need an interval to find an absolute max or min value of a function. Well, x, that side length, can't be 8. We kind of have to double that wire over to create the other side. So the biggest x could be is getting close to 4. The smallest x can be is close to 0. So we have our area function, 4x minus x squared. We have our interval, 0 to 4. Pause the video and see if you can, from here, finish the problem optimizing that area function on that interval. Find the derivative, find the critical points, and check the values of the area function at the critical points and endpoints. We'll check in a few seconds. This should go pretty quick. All right, welcome back. I like this as a starting example, since finding the derivative here doesn't require anything fancy. We don't need any use of the product, quotient, or chain rules. So if you calculate your derivative, you should find that it comes out to 4 minus 2x. That's a polynomial, so it's never undefined. We can jump straight to setting that derivative equal to 0. And if we do that, we get a very simple linear equation, 4 minus 2x equals 0, that has a solution of x equals 2. Now that's kind of half the answer for our question. Notice the question is asking for the dimensions. And for a rectangle, there are two different dimensions, the length and width. So we have, in this orientation, the length, x. We will want to figure out what the other dimension is, y, the height. And that's, again, where your constraint comes back into use. We determined 4 equals 4 minus x. That was from our constraint equation. And if we plug in x equals 2 to that constraint, we find that the y value also comes out to 2. So our dimensions that answer the question, well, it turns out to be the special case of a rectangle where the length and width are equal. The dimensions that maximize the area are 2 feet by 2 feet. And we were right. The biggest area we can create is that kind of a third configuration, a 2 by 2 rectangle, where the maximum area we can produce with a length of wire of 8 feet is 4 square feet. All right, now hopefully that wasn't too much to take in. Before we jump to example 2, make sure you thoroughly understand this since the problems start to kind of increase in difficulty. All right, with that in mind, let's proceed to our last example for this lecture. We'll save the really difficult examples for part 2. Example 2 is what I consider to be the intro to pizza box engineering. And that's actually like a real thing, packaging engineering. If you've ever been in a pizza shop where they take a flat piece of cardboard, there's little cuts made out of it, you fold it up and then you get a pizza box. That's actually a hard mathematical problem. We're gonna do the poorly designed pizza box here. You can see in the problem, we're gonna be creating an open top box. And of course, for pizza, we wouldn't want an open top, we would want a lid, but this puts us on the path to that. Now, if you're feeling adventurous, pause the video and give this an attempt. This one is kind of a little more difficult to sketch since it deals with a 3-dimensional object, a rectangular box. But if you're feeling, again, adventurous, give this a try. We'll check in a few minutes. All right, maybe you made an attempt at this. If you didn't, that's totally fine. Optimization problems are very difficult for most students. All right, so the first part is, let's just get an idea of what's going on in the problem. So the problem tells us that we have a square piece of cardboard with a given area. All right, how we create a rectangular box with no top is we're going to cut squares out of the corners. The remaining sides work as flaps that we're going to fold up. All right, and if you fold up those sides, we get this nice rectangular box, but there is no lid or top to it. All right, now let's kind of introduce some of the given information. We're told that the total area of this square piece of cardboard is 3,600 square inches. Now, since we're told the area, and we are also told that this piece of cardboard is a square, what we know is the area of a square is the side length squared. So we get this equation, L squared equals 3,600 square inches, and we can solve that for L, the side length of this entire piece of cardboard. Take the square root of 3,600 would be just 60. Might be easier to think square root of 36 is 6, and then tack on an extra 0. All right, so what we find for our sketch is that total side length is 60 inches. All right, that's going to play a role at some point. Now we can kind of vary the height of our kind of rectangular box depending on the size of the cut that we make in this. So we can either cut large squares out of the corners, or we can cut small squares out of the corners. What matters is the size or area that we're cutting out of the corners. And for the area there, since it's a square corner we're cutting out, what matters for a square is the side length. So let's say we're cutting out a square from the corner of side length x. This is our kind of second step of assigning variables. All right, so the corner we're cutting out has side length x. There's a top corner and bottom corner, if you look at that left side there. What's left in between those corners that are cut out is this length that we're labeling y. And that would be the length kind of the flap or the side. Now, if you fold this up, the corner that we cut out of side length x, fold that up, we would now have a box of height x. And then the side length y forms the base length and then depth there. All right, so we have two variables. X represents the kind of length of the square corner that we're cutting out, and that can vary. So we're denoting that by a variable. Now take a look at the end of the problem. It's asking us to maximize volume or find the dimensions of the box of maximum volume. All right, so what we want to do is come up with an equation or formula that relates the kind of side lengths to the volume of this object. And that's fortunately really simple. For a rectangular box or cube, the volume is length times width times height. All right, and if we multiply there, we have a height of length x. Because this was a square piece of cardboard, the remaining flaps there share the same side length, y. So we get for our total volume, x times y, or x times y squared. Again, there's the usual problem. This contains two variables. So we have to introduce kind of a what we're calling a constraint to eliminate one of these variables. All right, this is where your sketch comes in. There's a number of ways that you could do it for this problem. We started off by taking a look at the total side length for that square piece of cardboard, which was 60 inches. And depending on which side we're looking at, well, we have two squares we're cutting out. For instance, look on the left side. So two corners of side length x with a side length left of y. So what we get by looking at the side length is this constraint equation, 2x, that's x plus x for each corner that we're cutting out, and then plus y. We would want that total side length to equal the side length that we found, 60 inches. That's in order to use all of the cardboard material to create the rectangular box, which would thus maximize the volume. All right, now again, we can solve that for y. This is pretty simple, just subtract 2x. So we find y equals 60 minus 2x. We can again plug that back into our formula for the volume to reduce it from two variables down to a single variable. So if we go to our volume formula, V equals x times y squared, plug in y as 60 minus 2x. Now, this one's a little trickier to think about what range of values x can have. The smallest x can be is 0. We can cut very small corners out of the piece of cardboard. The biggest x can be is x can't be 60. Notice your sketch, we're cutting two corners out, and the biggest x could be, or get close to, is half that total side length. So half of 60 is 30. X can be any value getting close to 30 inches. So we have our volume function of just one variable x, which is x times 60 minus 2x, that quantity squared. And then our interval is 0 to 30. That is the hard part. If you got through all that up to there, you're in good shape for kind of the rest of the problems we'll be looking at. If you got stuck, chances are it was coming up with that volume formula. At this point, pause the video and see if you can make an attempt at finishing the problem, finding the absolute maximum, find the critical points. I'll give you a hint. Don't multiply that volume function out. See if you can differentiate it using a combination of product and chain rule. We'll check in a few minutes. All right, welcome back. If you use a combination of product and chain rule and simplify your derivative, you can factor out 60 minus 2x. A fully factored or simplified version should give you the derivative as 60 minus 2x times 60 minus 6x. You might, of course, have factored out some factors of 2 or factors of 6, but it's going to be equivalent to this. Now, at this point, this is a polynomial expression in factored form. It's going to be always defined, so we don't have to worry about the derivative being undefined to find a critical point. We can now just set that derivative equal to 0, and what we get are two solutions, two values for x. The first factor, 60 minus 2x equals 0, gives a solution of x equals 30. The second factor, 60 minus 6x, gives a solution of x equals 10 when we set that to 0. Now, we can kind of rule out x equals 30, plug that into your volume function, its formula. If you plug in x is 30, that gives a volume of 0. If you make x to be 30, you are cutting out the entire kind of piece of cardboard, so there's nothing left to fold up to give you a volume. So that kind of gives us something that's a little nonsensical. X equals 10 will correspond to our absolute max. Now that's just one of the dimensions. We still need y, but again, go back to your constraint. Now that you have x, you can plug that in to figure out your y value. Y we found was 60 minus 2x. If you plug in x is 10, you should find that y, the base side length, comes out to be 40 inches. So we get our dimensions, 10 inches by 40 inches by 40 inches. All right, that concludes part 1. These were the kind of simple examples, and then we also got through the intro and steps. In part 2, we'll be jumping straight to some more complicated examples, so make sure you thoroughly understand these before moving on to part 2.